So, next we look into the spatial or the Eulerian elasticity tensor. Okay. So, what we will attempt to do is we will try to find the spatial equivalent of this equation. Okay. That is the directional derivative of the second parallel Kirchhoff stress tensor in the direction of the displacement u equal to the double contraction of the Lagrangian elasticity tensor with the directional derivative of Green-Lagrange strain tensor in the direction of displacement. Okay. So, this is in the material frame, okay, or the undeformed frame of reference, okay, the initial configuration. So, now since the equilibrium equation is written in the current configuration or the spatial configuration, this equation has to be now transformed to the spatial configuration. Okay. So, you may be tempted to suppose that the spatial form of equation 9 would involve a relationship between the linearized Cauchy stress tensor and the linearized Almansi strain tensor, which is E. Okay. So, Cauchy stress tensor is sigma, because we had second parallel Kirchhoff and the Green-Lagrange strain tensors, two tensors which are entirely in the material configuration. It is error or not out of temptation that one can think that the spatial form of equation 9 would involve the linearized form of the Cauchy stress tensor and the Euler-Almansi strain tensor, which are the tensors entirely in the spatial configuration. Okay. But such a relation in principle can be achieved, but it would be very hard to deal with, okay, and will be very difficult to even understand, okay, how to go about. So, what we will do is we have to take a different route, and the different route is we have to interpret equation 9 in the rate form. Okay. Right now equation 9 is not in the rate form, which means you do not have velocity there, you have displacement. Okay. If you can interpret equation 9 in the rate form, then you can carry out the push forward operation of the resulting equation. Okay. Now, if you remember that we can linearize a tensor which has been linearized earlier with respect to displacement, we can also linearize that tensor with respect to the velocity. Okay. So, what we will try to achieve is linearize the second parallel Kirchhoff stress tensor and the Green-Lagrange strain tensor in the direction of velocity, okay, velocity v rather than the displacement. Now, what is the advantage? The advantage is we know that the directional derivative of a tensor in the direction of velocity is same as its material time derivative. Okay. So, we had earlier discussed in our overview of tensors that the directional derivative of a quantity in the direction of velocity is same as the material time derivative. Okay. So, remember we needed something in the rate form. Okay. So, we can get the rate, that is the material time derivative, when we linearize the second parallel Kirchhoff stress tensor and the Green-Lagrange strain tensor in the direction of velocity rather than the direction of displacement. Okay. So, now let us see what happens. If you take the directional derivative of the second parallel Kirchhoff stress tensor in the direction of velocity v, it gives you the material time derivative of S, that is the directional derivative of second parallel Kirchhoff stress tensor in the direction of velocity v will give you ds by dt, okay, which is the material time derivative of the second parallel Kirchhoff stress tensor. Similarly, if you take the directional derivative of the Green-Lagrange strain tensor in the direction of velocity v, okay, it will give you the material time derivative of the Green-Lagrange strain tensor. Okay. So, the directional derivative of E in the direction of velocity v is d E by dt. Okay. So, that is the material time derivative. So, now from equation 9, okay, if you remember our previous slides, equation 9 was the material time derivative of the second Pala-Kirchhoff stress tensor is the double contraction of the material elasticity tensor with the material time derivative of Green-Lagrange strain tensor. Okay, that was there. So, this we already know. Okay. So, now we also have seen that the push forward, okay, of the material rate of second Pala-Kirchhoff stress tensor is the Truesdell rate or the Kirchhoff stress tensor. So, when we were discussing kinetics, we discussed that the push forward, okay, so the push forward of the material rate of the second Pala-Kirchhoff stress tensor, which is shown here. So, this is a push forward operation. It gives you the Truesdell rate of the Kirchhoff stress tensor, and from this formula we know that you can relate the Truesdell rate of the Kirchhoff stress tensor to the Cauchy rate. Okay. So, that is the Truesdell rate of the Cauchy stress tensor, okay, and that is how you carry out the push forward of the material rate of second Pala-Kirchhoff stress tensor. Okay. So, now we also had seen that the push forward of the material time derivative. Okay. So, the material time derivative of the Green-Lagrange strain tensor is nothing but the rate of deformation tensor d. Okay. If you remember from our discussion in kinematics, the rate of deformation tensor d is the push forward of the material time derivative of the Green-Lagrange strain tensor, and the push forward is carried out using this particular operation. Okay. So, now if we take the push forward of equation 20. Okay. So, what is equation 20? This is the equation 20, okay, that we obtained from equation 18 and 19. Okay. So, if we take the push forward of equation 20, so that is if we take phi star S dot equal to phi star of C E dot, okay, then this is phi star of say C and phi star push forward of E dot. Okay. So, phi star of S dot, okay, will be nothing but j times of sigma 0. Okay. Let us call this sigma 0, and the push forward of the material time derivative of the Green-Lagrange strain tensor will be d, that is rate of deformation tensor, and let us define the push forward of material elasticity tensor as small c. Okay. Okay. So, remember I am putting 4 underbars for a 4th order tensor, okay, if you have to write in direct notation. So, in initial notation, okay, so what happens to this j, why it is missing? Because this has been, if you will see later, it has been absorbed in this spatial elasticity tensor C. Okay. So, therefore, if you write this expression in initial notation, sigma ij is Cij KL d KL. Okay. Here this C denotes the spatial or the Eulerian elasticity tensor. Okay. Now, this spatial or the Eulerian elasticity tensor, like its material counterpart, okay, which is this capital C, is nothing but a fourth order tensor. Okay. So, C is a fourth order tensor, this you can show. Hence, it can be expressed, okay, sorry, this is C in direct notation can be expressed as summation over I j k l C I j k l and the basis for a fourth order tensor, which is E I tensor product E j, tensor product E k, tensor product E l. Okay. And notice we have I, j, k and l all in lower case. This is because the spatial elasticity tensor resides in the spatial frame, and by convention we use lower case alphabets for spatial quantities. Okay. But the range of I, j, k, l will be 1 to 3. Okay. Now, this Eulerian or the spatial elasticity tensor C is defined as the Piola push forward of the material elasticity tensor C, and this spatial elasticity tensor is J inverse phi star, that is the push forward of the material elasticity tensor. Okay. So, the J that I was talking about in the previous slide is accommodated here. Okay. Now, we have to next try to establish the exact expression for 25. Okay. That is how to push forward. Okay, sorry, this is equation 26. Okay. So, right now this is only functional form, which means that the push forward of the material elasticity tensor will give you the spatial elasticity tensor. Okay. But actually, how do you carry out the push forward? Okay. So, to do this, let us see. Okay. So, let us start with the Truesdell rate of the Cauchy or the Piola-Kirchhoff stress tensor, which is given by following expression. Okay. Then you can write this in indicial notation. Okay. Tau I j is j sigma I j. Okay. This we already know. Again, we know that the Truesdell rate of the Kirchhoff stress tensor is nothing but F S dot F transpose. Okay. So, now my job is now to do everything in indicial notation. Okay. That would be much easier because we have a fourth order tensor here. So, the indicial notation of this will be sigma I j equal to F, and because the first index on the left hand side is I, so I should have I here, and then S dot resides entirely in the material configuration. So, I have capital I and capital J, let us say. So, there should be I here, and the next index here for F should be J, but because we have a transpose, this should be J and this should be J. Okay. No. Okay. So, this transpose will not be here. Yeah. So, the indicial notation for the relation between the Truesdell rate of the Kirchhoff stress tensor and the material rate of the second Piola-Kirchhoff stress tensor in indicial notation is given by following expression. Okay. So, let me just rub this, and this is what you can see here. Okay. So, that is what you can see here. Now, if I match these two expressions, so I can write J sigma I j is F I I S dot I j F j j. Okay. Which means that sigma I j is J inverse F I I S dot F j j. Okay. Now, I can just rearrange and take S dot ij on the right hand side. Okay. The next thing is, this is the push forward of the material rate, okay, of the Green-Lagrange strain tensor to give the rate of deformation tensor. So, the initial notation of this would be d I j, because d is a spatial tensor. So, lowercase f inverse, and because I is the first index, let me put I here, okay. But because this is inverse, I put f I I E dot I j f inverse j j, okay. So, and I can write the material time derivative of the Green-Lagrange strain tensor given by this expression. So, the initial notation of this will be E dot I j equal to f, and this would be lowercase I d I j f j j, okay. So, that is what we have in initial notation over here, okay. Okay. And now, because I already have an I j here, so what I do? I replace I j with another index k l, okay. So, according to our rules of initial notation, it is perfectly possible, okay. So, I have k l and small k l, okay. Now, what I do? I know this relation between the material time derivative of the second Piola-Kirchhoff stress tensor and the material time derivative of the Green-Lagrange strain tensor, okay. So, what I now do is, I write this in initial notation, okay, which is S dot I j is C I j k l E dot k l, okay. And now, in my previous slide, I have got the expression for E dot k l, okay. So, what I do now is, okay, if you see here, I had equation 27 where I had S dot I j, okay, and now S dot I j is C I j k l E dot k l, okay. So, this I can substitute here, okay. So, that is what we are doing, okay. So, we have C I j k l E dot k l, which is nothing but S dot I j. So, using equation 29 in equation number 27, I get this particular expression, okay. Now, I have E dot k l, okay, and from my previous slide, if you look closely, I have E dot k l is given by f k k f l l d k l, okay. So, this I can substitute here, okay, f k k, okay. So, f k k f l l d k l, okay, that is your E dot k l, okay. So, now what I get? I get an expression for relation between sigma I j and d k l, okay, and then I have this particular term, okay. Okay, so, this is say coefficient of d k l, okay. If you see this relation over here, okay, let me go back. Yeah, if you see this relation over here, so we had this relation, and also now we have got sigma 0 I j equal to one big expression d k l. So, if I compare both the sides, okay, if I compare both the sides, okay, so if I compare C I j k l is small c I j k l d k l, I can immediately identify this term in the bracket to be equal to Cij KL. Okay. So, Cij KL is J inverse Fii Fjj Cij KL Fkk Fll. Okay. So, if I take Cij KL totally on the other side, okay, on the right side. So, I get a very seemingly long expression for the component ijklth component of the spatial or the Eulerian elasticity tensor as this, okay, J inverse Fii Fjj Fkk Fll Cij KL. Okay. So, now if you know the expression for Cij KL, okay, so the tensor expression for Cij KL, you would use equation number 32 to get the spatial components of the Eulerian elasticity tensor. Okay. So, equation number 23 along with equation 32 is used as the fundamental constitutive equation that defines the material behavior. Okay. Now, if you use equation number 21 and equation 22, okay, we can see something, okay, we can relate whatever we got in the previous slide to the Lie derivatives. Okay. I hope you remember the concept of Lie derivatives. Okay. So, the Truesdell rate of the Kirchhoff stress is J sigma 0. Okay. And now, because the Truesdell rate is equal to the push forward of the material rate of the second Piola-Kirchhoff stress tensor. Okay. So, you have this. Also, d, that is the rate of deformation, is the push forward of the material time derivative of the Green-Lagrange strain tensor given by this following expression. Therefore, equation number 23, okay, which is the expression for the component of the spatial elasticity tensor in terms of the deformation gradient tensors and the component of the material elasticity tensor, can now be interpreted in terms of the Lie derivatives. Okay. And what is Lie derivative? Just to recapitulate what we had discussed in kinematics, for any tensor quantity G over the mapping psi, the Lie derivative of the tensor quantity G. Okay. So, G is a spatial tensor quantity. So, the Lie derivative of this spatial quantity G over the mapping psi will be nothing but the push forward of the material time derivative of the pullback of the spatial quantity. Okay. So, what it means? It is a 3-step process. The first, so the Lie derivative is a 3-step process. The first is the pullback, then you take the material time derivative, and then you have the push forward. Okay. So, using this and you knowing that S dot can be written as d by dt of S, and S is nothing but the pullback of the Kirchhoff stress tensor. Okay. So, if you look closely, this expression over here, it matches well with our definition of Lie derivative. So, the Truesdell rate of the Kirchhoff stress tensor is nothing but the Lie derivative of the Kirchhoff stress over the mapping psi, okay, where this expression has been used. Similarly, we know that the pullback of the Euler-Almansi strain tensor is nothing but the, so this is the pullback, this is nothing but the Green-Lagrange strain tensor. So, E dot here is nothing but d by dt of E. So, this d by dt is nothing but the material time derivative. Okay, although it's written as small d by dt, it is same. The meaning is same here as capital D by dt. Okay, so if we look again closely this expression, you will realize that this is nothing but the Lie derivative of the Euler-Allemandsi strain tensor, okay, over the mapping psi, and this gives you the rate of deformation tensor. So, using these two, okay, using this and this in our expression over here. Okay. So, J sigma 0 is the Lie derivative of Kirchhoff stress and D is the Lie derivative of Euler-Allemandsi strain tensor, and if you use these two here, you will realize that the Lie derivative of Kirchhoff stress over mapping psi is J sigma Jc double contracted with the Lie derivative of Euler-Allemandsi strain tensor over the mapping psi. Okay. So, this C establishes a relation between the Lie derivatives of the Kirchhoff stress tensor and the Euler-Allemandsi strain tensor. Okay. So, initially we said if somebody was tempted to think there will be a relation between the Kirchhoff or the Cauchy stress tensor and the material time derivative of the Cauchy stress tensor and the material time derivative of the Euler-Allemandsi strain tensor will give you the spatial elasticity tensor. It is not like that, it is actually the relation between the Lie derivatives of the Kirchhoff stress and the Euler-Allemandsi strain tensor respectively. Okay. So, let us derive the Lagrangian and the material elasticity tensor for a very simple material, okay, very simple class of material which are hyperelastic, and the model is given by the Saint-Venant-Kirchhoff material model. Okay. And for these material, the strain energy density function is given by this expression, where lambda and mu are the material constants. Okay. So, lambda and mu are here the material constants. So, your job is now to get the second Piola-Kirchhoff stress tensor expression and also get the expression for the material elasticity tensor. Okay. Now, how do we proceed? Okay. The first thing is we write this expression in the indicial notation, and remember Green-Lagrange strain tensor is in the material frame. So, all the indices will be in uppercase. So, the strain energy density potential is written as 1 by 2 lambda E k k E L L, okay, because trace of E is E k k. So, trace of E square will be E k k into E L L plus mu times E k L E k L. So, this is nothing but E double contracted with E, okay, and this is nothing but trace of E into trace of E. Okay. Now, we know that the second Piola-Kirchhoff stress tensor is given by following expression. Okay. If this is given by following expression, then what we need to do is we need to first write this in indicial notation. Okay. So, the indicial notation is Sij del psi by del E ij. Okay. And now, what we will do, we will put expression here into this particular relation. Okay. So, Sij, so we substitute the expression for strain energy potential in the expression for the second Piola-Kirchhoff stress tensor, and then Sij will be del by del E ij of 1 by 2 lambda E k k E L L plus mu times E k L E k L. Okay. And now, you can move this derivative inside and carry out the derivative. So, what you get if you move it inside, 1 by 2 lambda del E k k by del E i j into E L L plus 1 by 2 lambda E k k del ELL Eij plus mu times del EKL Eij EKL plus mu times EKL del EKL del Eij. Okay. And now we know that E del EKK by del Eij will be delta Ki delta Kj ELL, and this will be EKK delta Li. Okay. So, delta Li delta Lj, then mu delta Ki delta Lj EKL plus mu EKL delta Ki delta Lj EKL. Okay. Okay. Sorry. So, once you have this, you can use the substitution property of the Kronecker delta. Okay. So, if you see, look closely here, K is common. So, if you use the substitution property, it will be equal to delta Ij. Okay. Here also, if you look closely here, L is common. So, what you will get? Delta Ij, and here K will be replaced by I and L will be replaced by J. So, what you get is Eij, and similarly in the last expression you get Eij. Okay. So, these are, so you can add these two expressions, L and K are repeated index. So, it does not matter, you can replace this L with Kk, and what you will get, or you can replace this Kk with LL, and what do you get? Lambda delta Ij ELL plus 2 mu Eij. Okay. So, if you write this in direct notation, you will get S is lambda trace of E into second order identity tensor I plus 2 mu times the Green-Lagrange strain tensor E. Okay. So, that is the relation for the second Piola-Kirchhoff stress tensor, but you have been asked to get the Lagrangian elasticity tensor, for which again you have to take the derivative of this expression with respect to E. Okay. So, the Lagrangian elasticity tensor will be del S by del E. Okay. So, if we write in initial notation, we will have Cij KL del Sij by del E KL. Okay. Now, I can substitute the expression for second Piola-Kirchhoff stress tensor from the previous slide. Okay. And then I can open up the bracket. So, now you know how to take the derivative. Delta is constant, okay, lambda is constant, mu is constant. Okay. If you do this and realizing that because Eij is symmetric, this is like mu Eij plus mu Eji. Okay. So, we will on the simplification we will get Cij KL is lambda delta Ij delta KL plus mu delta Ik delta JL plus delta IL delta JK. Okay. So, this expression here is without the consideration of the major and minor symmetry. If you consider both the major and minor symmetries, that is symmetry of the second Piola-Kirchhoff stress tensor, that is Sij is Ji, and the Green-Lagrange strain tensor, that is EKL is ELK, then this following expression will boil down to Cij KL equal to lambda delta Ij delta KL plus 2 mu delta Ik delta JL. Okay. So, this relation for small deformation problem where the material configuration and the spatial configuration do not differ by much, in that case we can write this as Cij KL is lambda delta Ij, okay, delta KL plus 2 mu delta Ik delta JL. Okay. So, you will realize this if you have done a course on advanced solid mechanics, you will realize that this is nothing but the fourth order elasticity tensor that we studied. Okay. This is only when the material configuration and the spatial configuration do not differ by much. Okay. So, with this we end the first part of hyperelasticity. So, next we are going to start the derivation of the expression for the second Piola-Kirchhoff stress tensor and the material and spatial elasticity tensor for a specific class of hyperelastic material, which is Neo-Hookean material model. Okay. So, that is the most simplest form of model that can be used, and we will derive the expression for that particular model, and the later on the finite element formulation also will be based on this particular material model only. There are many more hyperelastic material model, but the duration of the course does not allow us to go much deeper. But whatever we will discuss in the next 2 lectures will help you to get the expressions for the second Piola-Kirchhoff and the material and the spatial elasticity tensors for other kind of hyperelastic material models. Okay. So, we are going to discuss the derivation for the Neo-Hookean material model. Thank you.